So this is lecture 34 on invariant maximality by Harvey Friedman, please.
Thank you. So, yes, I fixed the content of chapter 2. I had to spend some time uh, not completing the work discussed last time, but not in the notes for last time. I took it out. What's missing here is stuff about optimality of the N shift and N equivalence. This turns out to have a number of issues that I don't want to take the time to resolve right now. It may have to wait till after the book is done, or maybe at some point with a break uh, in with a break in the process of publication, I will come back to it. But right now, I'm fixing chapter 2, and I did have time to finish uh, a good part of it, polish a good part of it, but not all of it. So I think that one more lecture on chapter 2, with the hope of starting chapter 3, starting on chapter 3, will be done a week from today, or Thursday maybe of next week, the next lecture. So we have our usual, these are the chapters. I took the word derivations off here because I'm not going to do it. I'm not a little refurbishing. This is old. This is old. This is very old and very constant, the big reversal. This we started on, it's going to be revisited entirely in light of everything else. And then this hasn't really got started. So, all right, so I'm trying to finish this book, and it's going slow, but I think we're going to get accelerating going. We're going to get some acceleration. And then this is the slightly changed table of contents for chapter 2. Some uh, some small changes in the organization of the equivalences of all these different forms. We'll go through that a little bit, and then uh, we have these. This is what I didn't get a chance to completely polish up. This is for next time. I mean, this has been around for a long time, in some ways, years. This is the forward direction of stuff. That hasn't changed to what anything I said last time. And then, yeah, all that's the same. Okay. I don't know why this is so uh, space is unwanted here. This is something that was already discussed in a little different context in the 2025 version of this material, which is the old chapter 3 with local, now called local invariance. So this is completely unchanged. This is essentially unchanged, that almost every statement here, with exception of one, we know is implicitly pi 0, 1 over WKL naught. There's one we don't know the answer to that. But and then this is just a way of getting rid of the informal talk, like using omega 1 or using kappa. So this is just formal statements. And this is familiar from 2025, all this, nothing new. And now here's something new. So I've worked out completely, and we talk about today, the entire, the invariant maximality is on, I have this on minus n closed. If you remember, that's what we're doing, minus n closed. Well, why not look at all the rational intervals, wherever they are? And I worked this all out here today. I worked this all out which rational intervals can you use and which rational intervals can't you use? And this turns out to be a little involved, but with a nice conclusion, And then we want the link to the reversals. So we derive. So this is the new, slightly changed name. OISG means order invariant simple graph. Order invariant simple graph. This is a slightly different alphabetic combination of the old statement with cliques that was reversed in chapter 4, the reversal. So we want to derive the statement that was reversed. We want to derive it from all of the statements except one we don't know much about. I don't know that much about. All of the statements, including the lead statement and lead statements, seminal statement, all that. We want to show implies this. So therefore we have reversal of essentially everything in this chapter. And this chapter has the proofs of just about everything. It has the proofs of all the statements in the chapter. This chapter has proofs of all the statements in the chapter with omega 1 or with nothing or with large cardinals, with the SRP cardinals and so forth. So it has all that. And then the reversal is done by doing this here and just simply quoting chapter 4. Okay, so at the risk of a lot of repetition from last time, we have an introduction, which we haven't written for this because chapter was changed a lot. This is an old background stuff, having nothing to do, just Q comma less than stuff. Then we have maximality without invariance. And that can be done in RCA naught and so forth. Then let's go over this again because it's so critical. The lead statements of invariant maximality, the seminal statement uses n-shift invariance. This is the general notion of function invariance with ambient space. The n-shift, you take the tail and add 1 to all the coordinates in the n tail, so to speak. I don't use the definition of n tail specifically, but that's what I'm doing, right? I'm adding 1 to all the coordinates xj that are xi that are such that every xj is greater than or equal to xi lies in n. Such that all the coordinates greater than or equal to it lie in n, and I add 1. In shift of a set. So the seminal statement is every order invariant relation on every minus n and k has an n-shift invariant maximum chain. Yeah. I mean, I tried some other statements to be the seminal statement, and then I ran into a brick wall right now, and it's mentioned later, but this is the official one. All right, and then there's a variant where we strengthen the invariance from n-shift invariant to n-equivalent invariance by defining the definition of n-equivalent, which means that we're order equivalent and replacing everything in the n tail with something else with another element of n. Okay, and this is we discussed this a lot, the very natural equivalence relation. And this is stronger than the other thing. In other words, x and x, every x and its n shift or order are n equivalent, are capital N equivalent. Yeah. So then you have n equivalent invariance, it's called. Instead of n shift invariance, we have n equivalent invariance, right? Okay, and then we have the implication. N equivalent invariant implies n shift invariant, but we don't have the converse unless we're in the trivial dimension 1. And then this is the n equivalent invariant statement. So this is the first variant of the seminal statement. And we have the trivial implication, not the other way. The other way is established later. All right, so emulators is another idea which has its advantages and is my preferred way of dealing with people who are not really ready for abstract mathematics too much, like high school gifted. So emulator, but we've talked about this, and you have a finite set, and there's a notion of emulation and the maximal emulation, and we have this thing here, and also this one here. And these are all equivalent. We prove that. And then yeah, so we prove the equivalence of this by a chain of implications displayed in the headers below. Yeah, so we get all these equivalent by these chains. See all these implications. Okay, and then we introduce a new kind of statement, which is a uniform form of the others. First of all, this is a natural thing to talk about. Just do it on q to the k instead of on these intervals. This is a statement that I don't know. I don't know if the above is. I don't know the status of this. For a while, I thought that I could reverse this, but I don't know the status. I mean, I know it. I, we prove here that it follows from the seminal statement. You know, all the previous statements above. We prove that it follows, but we don't know it's strong. And we're going to give a uniform version. So we give a uniform version of this, which could also be viewed as a uniform version of this. And we prove it by a compactness argument. So we have a stronger statement. Here's the stronger statement using this obvious definition. Every order invariant relation R on every q to the k has an S contained in q to the k where each S restricted to less than or equal to n is an n shift or n equivalent invariant maximal chain in R less than or equal to n. In other words, there are two different forms depending on whether you pick this one or this invariance or this invariance. This invariance being stronger than this one. You see, that's kind of uniform. There's a uniformity in there beyond just the statement without the less than or equals, just the statement that I don't know the status of. This is a uniform form. And then this one, I do know that this is equivalent to the seminal statement and its cousins and its siblings, or what do you call it? Whatever you want to call it. First of all, I do prove here the triviality, which is that this stronger statement implies the weaker one. Well, without using the word stronger and weaker. You see, because this is a local form. This is a local uniform form. This is a uniform form. I don't know, maybe I should call this a local form. All right. I may a local uniform form or something. I may want to say a little bit more here because it's localized and it's uniform. So maybe I locally uniform or something. But anyways, it implies this, and you can't just do that by propositional by predicate calculus. You actually have to say something, and it's not much to prove this implication. This is the one. Repeat. This is the one that I don't understand yet, and this is the one I do understand and is equivalent. Yeah. So. So I have a section that yeah, I don't know what the order of ideas here is, but I proved that this is equivalent, and I prove everything in sight is equivalent, except for that one statement that I don't understand. Everything in sight is equivalent by by a big chain of implications. Here they are. Yeah, see this big chain of implications. You don't really have to pay much attention to this in detail. So one hunk of the chain of implications is done first, and then we take a breather and then do the rest of them here. And so they're all equivalent. Yeah, all equivalent. In particular, these are. In other words, this is the seminal statement. This is the seminal statement, and this is the this local uniform version or something. Yeah. All right, I'm going to play around with what English words I want to give. I used to call it the initialization. I may go back to that because it's both local and uniform. I don't know. But that's just expositional. I'm not talking about the content. There's this section on dimension reduction, which is expected. Anything in sight here done for dimension k plus one implies that it holds for k, that you can always do that. But you have to say it right. It's not that simple to say it right, so it covers all the cases. Uh, so yeah, I give the main cases that these are the ones where uh, yeah. Okay, and then we get into the proofs of the statements, which we don't need to talk about right now. I'll talk about it next time. I'll talk about this. There's nothing new in it. It's just organized, I think, in a very clean way, where I have 6 parts to each one, maybe 5 parts to each one, and they're done uniformly, independently, whether I'm doing one that's trivial, that's RCA naught, or whether I'm doing one that's omega 1 or doing one that's large cardinals. It's all kind of done uniformly. Uh, yeah, 5 parts. And I do it for the cardinal. Yeah. Okay. Uh, okay. And now we have this section called formalization in pi 0, 1. I think maybe I miss, maybe this should be formalization implicitly pi 0, 1 or something. Yeah. Maybe that's not copied right from the table of contents. All right, so implicitly pi 0, 1 falsifiability. If you remember, falsifiability is an important foundational idea. It means that you know a priori that if it's false, it's provably false. And this is an important idea in science. You have an hypothesis, and people like to check it against experimentation. Well, if you if it makes a prediction and you see the prediction is wrong, then you've refuted the statement. So there's a lot of scientific statements that can be viewed as falsifiable, and pi 0, 1 statements that are implicitly pi 0, 1. They don't have to be explicitly implicitly pi 0, 1. Like all of our statements are falsifiable. And I proved some theorem in here. This is old stuff. That implicit pi 0, 1 is equivalent, that falsifiability is almost equivalent, is roughly equivalent to being implicitly pi 0, 1. Roughly the same. I mean, there's a little bit of issues about whether you have induction in there or not. And then we show that almost all statements here are implicitly pi 0, 1. And that uses this idea of Gödel's incomplete. You use Gödel's completeness theorem. If you remember that, that goes way back. Use Gödel's completeness theorem to show that your statement is equivalent to formal consistency of some other statements. And then that makes it implicitly pi 0, 1. So we do that here. We have to do it here. We did it in the other context, and now we have to restate it or redo it. But I use the same lemmas and so forth. So there isn't anything really new here. And then this is a clean statement, formal statement of all the derivations we did. Clean statement of them. And then now here's something newish. So this is what I focused on after I failed to do some other things for this lecture. Um, so we want to know now invariant maximality. I mean, already you see that in the seminal statement, we're doing it on intervals minus n, right? Or minus n to the kth power. We're doing it on intervals, and minus n are very convenient and aesthetic. So now the natural question is, what other intervals can I use for this? Um, Now, I don't do a complete analysis of this in the following sense. I didn't address the question. I want to leave something open in this book, or I might come back to it. But it's clear that depending upon what the interval is, it's either outright false, well, we'll see that, or it follows, or it's equivalent uh, to one of the standard things. In other words, using minus one n to the k. It's either equivalent, or it might be weaker. You might be able to get away with using less axioms. You might be able to use less set theory to prove one of these things. In fact, this does come up, and I remark in passing about this. So you can ask the question, given an interval, what is the status of the statement for any fixed interval? But I don't really deal with that systematically. I just want to know the truth, and all the truth will obviously be in WKL naught plus con SRP as expected. All right, so we have the rational intervals. We know what they are. Okay, so we define what we mean by secured. Secured means that you can use it in here. It just means this. It means that the statement we're interested in holds for, okay, J is n shift, I'm sorry, n shift secured means you can use it with the n shift, and it's n invariant secured. Okay. If and only if you can use it, it's not n invariant, it's n equivalent. And n equivalent secured if and only if you can use it with n equivalence, right? And we say that J is n equivalent secured if and only if, whoops, can I repeat myself? We say that J is n shift secured. Say J, okay. All right. Now, n invariant secured implies n shift secured trivially because n invariance of a set implies n shift invariance. We remarked that earlier. So this is a stronger one. And then a lemma. See, I have to handle all these intervals with different kinds of endpoints and closed and open and right open and left open, and infinity is allowed and minus infinity is allowed. So it's a mess that has to be organized. So you need some general ways to do things to cut down the mess. So if J1 is contained in J2 and they have the same left endpoint and the same non-negative integers, then security is the same. And equivalent secured implies, I'm sorry, you only have one direction. And equivalent secured implies of J1 implies and equivalent secured of J2. I'm trying to remember if they have the same left endpoint. Isn't that an if and only if? Sometimes I get confused here. Same left endpoint and the same non-negative integers. Um, yeah, there was a problem. Yeah, there was a slight problem getting if and only if, and I didn't need to. I got away with just this. Yeah. We can see from the proof that it isn't obvious that it goes if and only if. Uh, but actually, I think after the fact, after I do all the classification, I think I should come back, which I didn't do, and say, oh, by the way, this is if and only if, but only after I did more work or something like that. But this is useful for getting the results. And then maybe you can go back and strengthen it. All right, so here, if you have an order in preserving isomorphism that maps the elements of J1 intersect N into an initial segment of the elements of J2 intersect N, then if J2 is secured, then J1 is secured. And if the elements of J1 intersect N are mapped onto the elements of J2 intersect N, then J1 is N equivalent secured if and only if J2 is N equivalent secured. These are easy things, but they're very useful cutting down the mess. All right, and then here we claim that these 5 intervals are secured. And this comes from looking at that. Remember, I had that chain, that long chain of implications. If you look at that long chain of implications, you can pull out this information here from that long chain of information. And this is where all the hard work is done. The work here is not really hard. It's it's a little bit more than you'd think you needed to do. But basically, the real work is in here, and that comes from that previous section about with that chain of implications, where the work is done in detail that we need to do. Okay, I defined left open to mean that the left endpoint is not an element. Left open means the left endpoint is not an element. Right open means the right endpoint is not an element. And remember, there are endpoints there. They have to be extended rationals. That's the definition of a rational interval with capital J. Every left open J is N invariant secured. This is proved. There's a lot of cases, but basically it boils down to these. I use these, and I use these other things about making the isomorphisms between things. So every left open J is N invariant secured. Now, you would barrel forward and do every right open J is N secured, but there's a bug in that, namely that this case of left N infinity, where N is greater than or equal to 0, it turns out everything's fine except that. Yeah, everything's fine except that. If the infinity is actually a number like 25.2, or even 25, then it can be done. Then there's no problem doing this. But the problem is with the infinity. Now that doesn't sound right. No, that is right. No, yeah, that is right. Yeah, because there's always stuff above. Yeah, that's right. Okay. Now, I should say something about this. The case that's non-trivial is, is when you have NP. Okay, so actually, this whole thing here is slightly non-trivial. If you go from N to P, where P is anything, and you're open, then if you look at it back, if you look at the interval backwards, it goes from essentially nothing up to N, where you have the indiscernibles on top, and in other words, it's a kind of reversal of order when you do N comma P here, where P is anything, P bigger than N, of course. And so you can turn it on its head and then do the construction going down. You can do the construction going down when we prove these things. And you do the construction going down and pick indiscernibles. That's how you prove this. And in fact, this argument will just need ACA prime, I believe, ACA prime. So there's an example, and I make this remark that you only need ACA prime to handle this n comma p. You don't actually do this using these. You do this, uh, uh, by redoing an argument from the basics. Except you don't use a large cardinal. You use the cardinal omega. It's a length omega thing, and then you use Ramsey's theorem. Yeah. But now the rest of it, the only other intervals are the bounded closed intervals. Bounded closed meaning you contain both endpoints. You you contain both endpoints. And also this exception here that we weren't able to handle. The reason we weren't able to handle this is because when you go backwards, this is not well founded. There's no start. And so therefore all the proofs that this is secured fail. Well, there's a reason why all the proofs that this is secured fail, because it's not secured. In other words, this can't be used. And I prove that. I could have put some more details on this about how I do it, but I try to be gentle in these lectures and just talk about the ideas and the lemmas. All right. Now, as a breather, okay, so we're looking at the case where we contain both endpoints, bounded closed, right? Okay. Now, yeah, so look at this. I guess maybe I didn't cover in this the case of P comma n, but that's all done also the same way. Okay, there's probably one case missing here that I have to fix, but it's not a serious case. It's easy. Uh, given what I'm doing here. So there's probably something else I have to do here. But anyway, so this one here, uh, this one here is okay. This one's fine. Uh, this one works because there's only two indiscernibles here, and you can't really say much. So I give an easy proof in RCN naught that this is n equivalent secured. And basically you look at n dot 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 n, and you look at the vector n plus 1 dot 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 plus n plus 1, and you'd like to throw them in to the maximal chain right away. Well, you can if the relation holds between those two types, right? And and then you're fine. But if the relation doesn't hold between the two types, then you throw in n plus a half dot 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 comma n plus a half, and then that will once you throw that in, that will ruin. You can't throw in the n comma through n and the n plus 1 through n plus 1. You can't throw them in because of the incompatibility with R, with the relation. And so then it's again n equivalent, because that's the only thing that the n equivalent means. Uh, you see, the n equivalence is trivial inside this interval. It only has that one case. You don't have anything else because you have to move the top one some. You can't do that. Yeah. Okay. All right. So move top one to other non-negative integers, and you don't have them here. You're just, you know. Okay, so here, what about if these intervals are at least of length 2? Well, now we finally have something that we can refute. So I refute this by an argument actually that comes up in the 2025 version of the book where I was doing stuff connected with uh, finite usability. It's the same construction, same tricky construction. So I proved that this is not N-shift secured. And then finally, these are shown to be not N-shift secured by another technique. Uh, this involves making the relation on pairs, say that the intervals, that the closed intervals, the associated closed intervals pairwise intersect. Then you can show that that really is just the set of all open intervals. The maximal chains are the set of all open intervals, non-empty open intervals, whose which contain a fixed real number in its closure. So you have a fixed real number greater or equal to zero, and you have all the intervals that contain it, and that's the maximal chain. It has to have that form, and then but that never can be, n-shift invariant, never. Okay, because it has pairs of points with the left endpoint zero, with the first coordinate zero, and then you can just shift them out uh, so that the left endpoint is higher than the real number x that I told you about, that real number x, so that it's higher than that. So therefore, you have a contradiction. So this is a technique for showing this is bad is quite different than the technique for showing this is bad. So now we finally have the upshot of all of this with the rational intervals. So every rational interval is n-shift and n-equivalent secured with the sole exceptions of the closed intervals nm, n infinity, where m is greater than or equal to n plus 2, n greater than n, why not go to n, and n greater than or equal to 0. These exceptions are neither n-shift nor n-equivalent secured. Neither they're bad even for n-shift. Yeah, because the shifting is enough to get the contradiction. All right, now finally, this is the last section in this chapter. So this is how I link, how do I reverse everything in this chapter? So I show that it implies something that we already reversed, which is in chapter 4. So recalling chapter 4, now people reading this book from the front to the back are not going to recall chapter 4 when they're looking at chapter 2, but we can do that between you and me. In chapter 4, recall that we reversed these two statements. These two statements, okay, this is OSIG is a new thing. It's called order is a new acronym. It's not a new. Order invariant simple graphs, OISG. Uh, and we use the word clique. You know, clique is the same as a chain. In other words, a chain and a graph is the same as a clique. Okay, and remember we had this notation. Every order invariant graph has a on here has a invariant maximal clique. And then making n and k, the two variables n and k equal, is just this. This is just a special case of this when they're equal. And we actually reversed the weaker one, which is always nicer. We reversed the weaker one. And now let's recall the definitions for this. The definitions. So we use F invariance as we always have. Um, oh, no, we use F invariance when F is just a mapping of one dimension. Yeah, maybe I should call, I don't know, local, maybe I should, remember, since now the book has these two big different things, local and global theory, so to speak. Probably F invariant, maybe locally F invariant. I don't know what I'm going to do. Anyways, it's not important right now. All right, so we have a partial map, one dimension, and we have this. This is the definition of the of the rest of the book, you know, of the book starting at chapter 4. This is the starting as the new chapter 4. This is the definition of the book. This is the local invariance notion. All right, so which is a one-dimensional animal. And then continuing, this is a particular bijection that we use. This is all old stuff from last year. This bijection, and it's the identity on -1, 0, and maps each pi to pi plus 1. And the definition of a simple graph, we know about that, irreflexive and symmetric relation, and a clique. And here's the definition of order invariant graph. Just means the adjacency relation is order invariant. Okay, and now we have the reversal from chapter 4. It's section 11, the 24th statement in the section 11 of chapter 4 is this, that OISG max clique implies con SRP. And I actually did an RCA naught, which is nice. It's not essential, but I bothered to show that. You know, the natural place to do this is WKL naught, and even more natural is a little higher, even than that, but it can be done in RCA naught. So I do that. That's from the old chapter 4. And now we want to link the reversal with the statements in this chapter. So we actually prove this. This is what we do. So we prove that our statement here, our seminal statement, we prove that our seminal statement implies this statement. And the way I do that, this is pretty easy, is I assume that this is true, and then I start with a ordered varied graph on -1, 1, and I turn it into a relation, the same relation. I turn it into a relation on -n to the k by multiplying through by n. Just multiply through by n, and you get a graph on -n and k. Well, now you think of it as just the adjacency relation, the relation, and that's order invariant also. And then you take a maximal clique, excuse me, a maximal chain in this thing and that lives in -n to the k. You take a maximal chain in there, and now that's obviously going to be nothing more. The maximal chains in there are nothing more than n times the maximal cliques in the original graph we're interested in. See, the correspondence is just multiplication by n. And then the maximal chains are just multiplied through by n. And then the invariance under n shift is actually stronger. It's actually stronger. The invariance under n shift has as a special case this thing here, invariance with respect to this thing here, because it's just shifting. The shifting the shifting up here, the shifting in the definition of this function up here, the shifting just corresponds to the shifting by 1 up here that we do, that's familiar, right? And yeah, so all we have to do is have it be the identity, not move any of these. But that's what the n shift does. It's not going to move any of the negative numbers because the negative numbers can't be non-negative integers because they're negative numbers. Okay, so this invariance here is special case of this invariance. After you multiply through by n, it's a special case. So that's how you easily prove that this implies this. See, this is somewhat stronger because you can go up higher and then have these numbers that are not integers, not numbers, they're higher and they're fixed and these are moved. But here you can only Down here, in here, you only can move. You're only talking about fixing the negative numbers. So this is weaker than this. This is stronger than this. All right. Anyways, this implies this is the right direction of implication. And so since we chapter 4 from last year reversed this, this reverses this, and all the statements we did are equivalent to this, except one that we don't know about, as I told you. Yeah. So that's all I want to say. I'm letting you off easy today. Andreas, we're done.